Copernicus heliocentric model. Galileo observed Jupiter's moons, lunar craters, and the phases of Venus, thereby demonstrating concretely that celestial bodies did not revolve exclusively around Earth. Despite significant opposition and religious controversy, Galileo's persistent scientific advocacy paved the way for modern observational astronomy and experimental physics. Isaac Newton's development of classical mechanics and his universal law of gravitation unified celestial and terrestrial phenomena under a single theoretical framework. Newton's Principia Mathematica profoundly impacted physics by providing mathematical foundations to explain planetary orbits, tides, and projectile trajectories. Newtonian mechanics dominated scientific thought for nearly 3 centuries, underpinning the Industrial Revolution and facilitating technological advances ranging from machinery to space exploration. The 19th century saw revolutionary insights into electromagnetism through the work of Michael Faraday and James Clerk Maxwell. Faraday's experiments demonstrated the principles of electromagnetic induction, essential for electricity generation and the technological applications that power modern civilization. Maxwell mathematically unified electricity and magnetism into a cohesive electromagnetic theory, culminating in the prediction of electromagnetic waves. This theoretical prediction laid groundwork essential for the development of radio, television, wireless communication, and eventually the concept of fields fundamental to modern physics. Charles Darwin's theory of evolution by natural selection profoundly transformed biology, anthropology, and the philosophy of science. Darwin posited that species evolved through heritable variations and differential reproductive success, radically changing humanity's understanding of biological diversity and origin. Evolutionary biology provided critical insights into genetics, ecology, medicine, and environmental sciences, fundamentally reshaping modern scientific and philosophical discourse. At the dawn of the 20th century, quantum mechanics emerged as a revolutionary paradigm shift, challenging classical physics' deterministic worldview. Max Planck introduced the concept of energy quantization to resolve inconsistencies in classical thermodynamics and electromagnetic radiation. Subsequently, Niels Bohr developed quantum models of atomic structure, and Werner Heisenberg and Erwin Schrödinger formulated complementary mathematical frameworks that introduced probabilistic interpretations and uncertainty into physics. Quantum theory revolutionized fields including chemistry, materials science, computing, and cryptography. Simultaneously, Albert Einstein fundamentally altered the perception of space and time through his theories of special and general relativity. Einstein's special relativity established the constancy of the speed of light and revealed the interdependence of space and time, introducing mass-energy equivalence encapsulated in the iconic equation E equals mc squared. General relativity further advanced this revolution by describing gravity as the curvature of spacetime due to mass and energy distribution. The predictions of general relativity, such as gravitational lensing and gravitational waves, have since been experimentally confirmed, further enriching cosmology and astrophysics. In genetics, the discovery of the structure of DNA by James Watson, Francis Crick, Rosalind Franklin, and Maurice Wilkins unveiled the molecular mechanisms underpinning heredity and biological function. The double helix structure explained how genetic information is encoded, copied, and transmitted through generations, fueling advancements in molecular biology, biotechnology, medicine, and forensic science. DNA sequencing and genetic engineering, products of this discovery, have transformed fields ranging from agriculture to personalized medicine. Another pivotal breakthrough came with the development of plate tectonics theory in geology during the mid-20th century. By synthesizing evidence from continental drift, fossil distribution, volcanic activity, and seafloor spreading, scientists like Alfred Wegener, Harry Hess, and J. Tuzo Wilson developed a unified model explaining the dynamic nature of Earth's lithosphere. Plate tectonics has profoundly influenced our understanding of Earth's geological history, earthquakes, volcanic eruptions, and the formation of natural resources, critically shaping approaches to environmental management and disaster preparedness. Advancements in cosmology toward the late 20th century, such as the discovery of cosmic microwave background radiation by Arno Penzias and Robert Wilson, provided compelling support for the Big Bang theory. This discovery solidified the understanding of the universe's early history and facilitated subsequent explorations into cosmic structure formation, dark matter, and dark energy. The revelations concerning the accelerating expansion of the universe, evidenced by observations of distant supernovae, indicated the existence of dark energy, prompting new theoretical and experimental approaches in physics. Breakthroughs in particle physics, such as the discovery of subatomic particles like quarks, leptons, and bosons, including the Higgs boson at the Large Hadron Collider in 2012, deepened the understanding of fundamental forces and matter's underlying structure. The Standard Model emerged as a robust theoretical framework, accurately describing particle interactions and offering predictive power validated by experimental results. Despite its successes, ongoing research into phenomena such as neutrino oscillations, dark matter, and antimatter asymmetry continues to challenge and expand contemporary physics frameworks. In the 21st century, emerging scientific discoveries increasingly blur the boundaries between disciplines. CRISPR-Cas9 gene editing technology, discovered and refined by Jennifer Doudna, Emmanuelle Charpentier, and Feng Zhang, revolutionized biology by providing precise tools to edit genetic information. Its potential applications range from curing genetic diseases to advancing agricultural productivity and bioengineering organisms for medical and environmental purposes. Another significant contemporary advancement is artificial intelligence, particularly deep learning and neural networks, enabling unprecedented data-driven insights across science. AI-driven techniques now accelerate drug discovery, model complex systems, optimize energy management, and drive advancements in robotics, astronomy, and climate science. Contemporary astronomy continues to yield transformative insights. Detection of thousands of exoplanets by the Kepler Space Telescope and subsequent observatories has reshaped humanity's perspective on the potential abundance of habitable worlds and the possibility of extraterrestrial life. Complementing this, advancements in astrophysical simulations and multi-messenger astronomy have deepened understanding of extreme cosmic phenomena, including neutron star collisions and black hole mergers observed through gravitational wave detectors such as LIGO and Virgo. Moreover, advancements in renewable energy and energy storage technologies continue reshaping societal approaches toward sustainability and climate change mitigation. Breakthroughs in battery technology, photovoltaics, and advanced materials hold promise for reducing carbon emissions, revolutionizing transportation, and supporting sustainable energy infrastructure. The continuous interplay between discovery, technological application, and interdisciplinary collaboration propels humanity toward greater understanding of natural phenomena and potential innovations. The convergence of quantum computing with classical information technology represents another significant frontier. Quantum computers harness quantum mechanical phenomena such as superposition and entanglement to perform complex computations exponentially faster than classical computers. Recent advancements by companies and research institutions have demonstrated quantum supremacy, where quantum processors perform specific calculations beyond classical computing capabilities. Potential applications include cryptography, drug discovery, materials science, optimization of complex logistical networks, and the simulation of molecular interactions and quantum systems. Neuroscience has similarly undergone profound advancements, driven by new technologies like functional magnetic resonance imaging, fMRI, optogenetics, and brain-computer interfaces, BCIs. Optogenetics, which allows precise control of neurons using genetically encoded light-sensitive proteins, has revolutionized the study of neural circuits, behavior, and neurological diseases. Brain-computer interfaces offer promising avenues for restoring mobility and communication to individuals suffering from paralysis, neurodegenerative diseases, or severe injuries, highlighting the potential for technology to transform human quality of life. Further exploration in synthetic biology has expanded the boundaries of life sciences by engineering biological systems with novel functions. Synthetic cells and organisms designed for minimal genetic components have provided insights into fundamental biology and potential practical applications such as biofuels, bioplastics, biosensors, and personalized medicine. These advancements pose significant ethical and philosophical questions, redefining our understanding of life's boundaries and humanity's relationship to nature. Environmental science and climate research have significantly benefited from advancements in satellite technology, remote sensing, and global climate modeling. Comprehensive climate models have improved predictions of global temperature changes, extreme weather patterns, and the ecological impact of human activities, informing international climate policy and adaptation strategies. Additionally, breakthroughs in carbon capture, geoengineering techniques, and ecological restoration offer potential pathways to address anthropogenic climate change, though their implementation raises complex ethical, economic, and environmental considerations. In materials science, the discovery and characterization of novel two-dimensional materials like graphene have stimulated research in nanotechnology and electronics. Graphene's remarkable strength, electrical conductivity, flexibility, and thermal properties have inspired the development of new electronic devices, flexible displays, sensors, high-performance batteries, and advanced composites. Beyond graphene, other materials, such as transition metal dichalcogenides and topological insulators, are also opening unprecedented opportunities for innovation in quantum electronics and spintronics. Astronomical instrumentation and space exploration continue to push scientific frontiers further into the cosmos. Powerful ground-based telescopes, such as the Extremely Large Telescope, ELT, and advanced orbital observatories like the James Webb Space Telescope, JWST, significantly enhance humanity's capacity to observe distant galaxies, planetary systems, and the early universe with unprecedented resolution and sensitivity. Robotic missions to Mars, Europa, Titan, and asteroids advance understanding of planetary formation, habitability, and the potential distribution of life within our solar system and beyond. Meanwhile, biotechnology's innovations in tissue engineering and regenerative medicine have opened new horizons for therapeutic interventions. Advances in stem cell research enable scientists to generate functional tissues and even organoids in laboratories, facilitating novel treatments for organ failure, injuries, and degenerative diseases. These technologies hold great promise for personalized medicine, offering tailored therapeutic approaches based on individual genetic profiles and physiological conditions. In mathematics, significant progress in computational algorithms and complexity theory continually reshapes fields such as cryptography, data science, and theoretical computer science. Breakthroughs in number theory, such as the resolution of long-standing conjectures, provide deeper insights into mathematical structures, influencing diverse scientific disciplines ranging from physics to economics. Computational mathematics and machine learning algorithms further amplify human capabilities in tackling problems previously deemed intractable, driving advances across scientific domains. Finally, interdisciplinary efforts in complex systems science, examining ecosystems, social networks, economies, and even consciousness itself, provide crucial frameworks for understanding emergent behaviors and self-organizing dynamics. The integration of complexity theory with computational modeling enables scientists to approach global challenges such as pandemics, urbanization, economic inequality, and ecological collapse through innovative analytical lenses, suggesting novel strategies for sustainable management and resilience. Collectively, these ongoing scientific endeavors highlight humanity's relentless pursuit of knowledge, continually redefining our place in the universe and profoundly influencing future generations. Advancements in robotics and automation continue to profoundly reshape both industry and society. Robotics now extend beyond traditional manufacturing roles into healthcare, agriculture, environmental monitoring, and even disaster relief. Surgical robots enable unprecedented precision during complex medical procedures, significantly reducing human error and improving patient outcomes. Agricultural robots equipped with sophisticated sensors and machine learning algorithms optimize crop yields, manage pests sustainably, and reduce the environmental footprint of farming practices. Autonomous drones and robots perform hazardous tasks in disaster zones, detecting survivors, delivering critical supplies, and mitigating risks to human rescue workers. Simultaneously, the development of autonomous vehicles promises to transform transportation infrastructures, urban planning, and energy consumption. Self-driving technologies integrate advanced sensors, artificial intelligence, and real-time data analytics to navigate complex environments safely. Widespread adoption of autonomous vehicles has the potential to reduce traffic accidents, enhance mobility for elderly or disabled populations, lower urban congestion, and significantly decrease greenhouse gas emissions through optimized routing and electrification of transportation systems. The field of renewable energy continues to expand rapidly, driven by groundbreaking innovations in photovoltaic materials, wind turbine technology, and energy storage systems. Perovskite-based solar cells offer significantly improved efficiency at lower manufacturing costs, potentially revolutionizing energy generation capabilities worldwide. Innovations in offshore wind technology enable harnessing wind energy more efficiently, contributing substantially to global efforts toward decarbonization. Advanced battery chemistries, including solid-state batteries and sodium-ion technology, promise improved energy density, longer lifetimes, and reduced environmental impacts, facilitating broader adoption of renewable energy sources. Recent breakthroughs in artificial photosynthesis, which emulate natural processes to convert sunlight directly into chemical energy, such as hydrogen fuel, open new pathways toward sustainable fuel generation and carbon capture technologies. Researchers developing these technologies seek solutions capable of addressing energy needs sustainably while mitigating climate change through direct conversion of carbon dioxide into useful materials or fuels. Space exploration continues to achieve new milestones, fostering unprecedented scientific collaborations and technological advancements. The recent growth in space commercialization, exemplified by private companies launching reusable rockets, conducting orbital missions, and preparing crewed expeditions to the Moon and Mars, marks a fundamental shift in humanity's relationship with space. Long-duration human spaceflight, including planned missions to establish permanent settlements on the Moon or Mars, stimulates advancements in life support systems, radiation shielding, regenerative agriculture, and habitat engineering that may have significant implications for sustainability and resource management on Earth. Astrobiology and the search for extraterrestrial life represent a frontier increasingly informed by recent discoveries. Evidence of water-rich environments beneath the icy crusts of moons such as Europa and Enceladus, as well as detection of organic molecules on Mars and Titan, fuel hypotheses about the existence of microbial life beyond Earth. Advanced telescopes and spectroscopic techniques aim to identify biomarkers on exoplanets, potentially revolutionizing human understanding of life's diversity and origins within the universe. Nanotechnology continues to expand the horizons of materials engineering and medicine. Nanomaterials with unique optical, electrical, magnetic, and catalytic properties offer revolutionary applications, from targeted drug delivery systems to highly sensitive diagnostic tools and sensors. Nanofabrication technologies allow researchers to construct materials and devices at atomic scales, facilitating breakthroughs in quantum computing, nanoelectronics, and energy harvesting applications. Advancements in oceanography and marine biology have illuminated Earth's oceans' vital roles in climate regulation, biodiversity conservation, and global biogeochemical cycles. Innovative deep-sea exploration vehicles and autonomous underwater robots enable scientists to study remote marine ecosystems, discovering previously unknown species and providing insights into the resilience of life under extreme conditions. Marine genetic resources, particularly extremophiles thriving around hydrothermal vents, inspire new bioactive compounds with pharmaceutical and industrial potential. Furthermore, groundbreaking research in microbiology continues to reshape our understanding of health, ecology, and evolution. Studies into the human microbiome reveal its fundamental role in human immunity, metabolism, and even behavior, suggesting novel therapeutic interventions for chronic diseases, obesity, and mental health disorders. Similarly, microbial ecology provides insights into ecosystem function, nutrient cycling, climate change adaptation, and the potential for bioremediation of pollutants. Parallel progress in cognitive sciences deepens our understanding of human consciousness, learning processes, memory, and decision-making. Integrating neuroscience with artificial intelligence and philosophy fosters increasingly sophisticated models of cognitive processes, inspiring advances in educational technologies, mental health interventions, and human-machine interactions. Together, these evolving scientific frontiers embody the relentless drive of human curiosity and innovation, continuously redefining the boundaries of knowledge and opening new realms of possibility for future generations. Advancements in fusion energy research represent one of the most ambitious scientific quests aimed at addressing humanity's growing energy demand sustainably. Fusion power, replicating the nuclear processes fueling stars, offers the potential to deliver virtually limitless, clean, and safe energy without the persistent waste and proliferation concerns associated with conventional nuclear fission. Recent progress in magnetic confinement fusion, exemplified by international efforts such as the ITER project, demonstrates critical advancements in plasma physics, superconducting magnet technology, and materials capable of withstanding extreme temperatures. Simultaneously, innovations in inertial confinement fusion, using powerful lasers and particle beams, have brought humanity closer to achieving net energy gain, potentially revolutionizing energy infrastructure worldwide. Parallel developments in quantum materials science promise to revolutionize technology at a fundamental level. Topological quantum materials, superconductors operating at higher temperatures, and exotic materials exhibiting quantum spin liquids hold promise for next-generation electronics, ultra-fast computing, and high-efficiency energy transmission. Researchers exploring superconductivity at room temperature have begun to overcome barriers previously thought insurmountable, paving the way for revolutionary impacts across power distribution, transportation, and communications technologies. The ability to engineer quantum states of matter precisely, such as Majorana fermions in nanowires, also advances prospects for scalable quantum computing and inherently secure quantum communication networks. Breakthroughs in gravitational wave astronomy represent another transformative development reshaping astrophysics and cosmology. The direct observation of gravitational waves by LIGO and Virgo collaborations not only confirmed Einstein's predictions but also opened entirely new observational windows into phenomena previously hidden from traditional electromagnetic observation methods. Detection of neutron star mergers through multi-messenger astronomy, combining gravitational waves with electromagnetic signals, has provided unprecedented insights into cosmic nucleosynthesis, revealing the origins of heavy elements like gold, platinum, and uranium. Planned future gravitational wave observatories, both terrestrial and space-based, such as LISA, promise to probe deeper into cosmic history, shedding light on early universe conditions, black hole populations, and fundamental tests of gravity and spacetime geometry. Emerging fields in artificial life and synthetic consciousness further challenge conventional boundaries between biology, computing, and philosophy. Scientists now actively design artificial neural networks capable of exhibiting emergent behaviors, problem-solving skills, and even forms of synthetic intelligence reminiscent of rudimentary biological cognition. Research into artificial cells and protocells, minimalistic synthetic systems capable of growth, replication, and evolution, raises profound questions regarding definitions of life itself. These endeavors provoke deep philosophical and ethical discussions about the potential consequences of creating new life forms or forms of intelligence, potentially reshaping society's relationship with technology and the natural world. In biotechnology, recent advances in precision medicine, epigenetics, and gene therapy offer transformative prospects for personalized healthcare. Epigenetic research has deepened understanding of gene-environment interactions, influencing how scientists approach complex diseases, aging processes, and even mental health disorders. Gene editing tools, like base editors and prime editing, further refine CRISPR-Cas9 technology, enabling the precise correction of genetic mutations without unintended genomic alterations. Therapeutic successes in treating diseases such as sickle cell anemia, hemophilia, and genetic blindness highlight the immense potential of genetic medicine, underscoring transformative possibilities for global health and human longevity. Additionally, the emergence of quantum biology, the study of quantum effects in biological systems, offers a novel paradigm bridging biology, physics, and chemistry. Investigations into photosynthesis have revealed quantum coherence processes enhancing energy transfer efficiency within biological systems, challenging traditional classical interpretations of biochemical reactions. Quantum phenomena might also play crucial roles in enzyme catalysis, bird navigation, olfaction, and even neurological functions, inspiring innovative approaches for biotechnology and medicine. Breakthroughs in climate engineering research, including carbon dioxide removal, CDR, and solar radiation management, SRM, present potential interventions to mitigate climate change impacts. Methods such as direct air capture technologies, enhanced weathering, bioenergy with carbon capture and storage, BCCS, and ocean fertilization strive to actively remove CO2 from the atmosphere, addressing accumulated greenhouse gas emissions. Meanwhile, approaches like stratospheric aerosol injection, cloud brightening, and reflective surfaces aim to reduce solar radiation reaching Earth's surface, raising crucial ethical, geopolitical, and environmental considerations regarding their governance, implementation risks, and long-term consequences. Ocean-based renewable energy research, including wave, tidal, and thermal gradient energy, expands the diversity of sustainable energy sources available for global adoption. Advances in materials science, marine engineering, and energy storage solutions now enable more efficient and resilient energy harvesting from oceans. Coupled with ecological restoration practices such as marine permaculture, these initiatives promise synergistic benefits, offering sustainable food production, carbon sequestration, and energy generation simultaneously. Progress in computational neuroscience and neuroinformatics continues to illuminate the intricate complexities of the human brain. Ambitious projects like the Human Brain Project and Brain Initiative utilize cutting-edge imaging techniques, computational modeling, and artificial intelligence algorithms to map neural circuits comprehensively, decode cognitive processes, and understand consciousness more deeply. This expanding neuroscientific knowledge underpins revolutionary applications, including brain-inspired computing architectures, neuromorphic engineering, advanced neuroprosthetics, and treatments for neurological disorders, fundamentally transforming human capabilities and interactions with technology. In fundamental physics, ongoing research into dark matter and dark energy remains one of the greatest scientific mysteries. Experiments in particle physics, astrophysics, and cosmology, including dark matter detection experiments, e.g., Xenon and LUX Zeppelin, astronomical surveys, Euclid, Vera Rubin Observatory, and high-energy particle accelerators, continually refine constraints on the elusive nature of dark components of the universe. Resolving these mysteries could lead to revolutionary shifts in the understanding of fundamental physics, prompting the development of entirely new theories beyond the standard model and potentially altering humanity's perception of cosmic structure and evolution. Interdisciplinary advances in complexity science increasingly transform approaches toward global sustainability, economics, and social dynamics. Complex adaptive system frameworks, integrating insights from physics, ecology, sociology, economics, and computer science, allow for the modeling of human societies, economic markets, ecosystems, and climate dynamics with unprecedented detail and accuracy. These methods enable researchers and policymakers to anticipate critical transitions, optimize resource management strategies, and develop resilient societal infrastructures capable of adapting to rapid technological, environmental, or social change. Collectively, these expanded scientific frontiers illustrate the remarkable depth and interconnectedness of modern scientific inquiry. Each discovery not only extends human understanding but also generates entirely new fields of exploration, continually redefining humanity's role within an increasingly complex and interconnected universe. Recent advances in immunology and vaccine development have transformed medical science by significantly enhancing human capabilities to combat infectious diseases and cancer. Breakthroughs in mRNA-based vaccines, highlighted by their critical role in controlling the COVID-19 pandemic, demonstrated unprecedented efficiency in rapid vaccine design, production, and deployment. This revolutionary technology is now applied to combat a range of illnesses, including influenza, HIV, malaria, and various cancers. Coupled with improvements in immunotherapy, such as checkpoint inhibitors and CAR T-cell therapies, these advances have substantially improved outcomes for patients suffering from previously untreatable or refractory malignancies. Simultaneously, developments in proteomics, metabolomics, and bioinformatics have expanded our understanding of biological systems at the molecular level. Advanced mass spectrometry techniques and computational algorithms now enable comprehensive analysis of proteins and metabolites in health and disease states, offering powerful diagnostic tools and therapeutic targets. Personalized medicine increasingly leverages these omics technologies, integrating genomic, proteomic, and metabolic data to precisely tailor interventions to individual patient profiles, thereby optimizing efficacy and minimizing adverse effects. Significant innovations in agricultural biotechnology promise to address global challenges in food security, environmental sustainability, and climate resilience. Genetic engineering techniques, including gene editing via CRISPR-based methods, have enabled the development of crop varieties resistant to diseases, pests, drought, and soil salinity. Bioengineered plants exhibiting enhanced nutritional profiles or reduced environmental impact further exemplify the transformative potential of modern agriculture. Concurrently, emerging approaches like precision agriculture and vertical farming utilize robotics, artificial intelligence, and hydroponics to optimize resource usage, significantly reducing agricultural footprint and environmental degradation. Advances in atmospheric and environmental chemistry continue to enhance understanding of Earth's biosphere-atmosphere interactions, particularly regarding pollutants, aerosols, and climate-active gases. Sophisticated monitoring systems utilizing satellite remote sensing, drone-based sensors, and ground-based networks provide detailed, real-time data to better assess air quality, greenhouse gas emissions, and pollutant dispersion. Insights from these data inform international policy initiatives, urban planning decisions, and climate mitigation strategies, helping societies move toward sustainable ecological stewardship. In planetary science and astrobiology, ongoing missions significantly enrich understanding of solar system history, habitability, and potential extraterrestrial biospheres. Robotic exploration of Mars by NASA's Perseverance rover and China's Tianwen-1 mission has yielded crucial evidence about ancient environments potentially favorable to microbial life. Upcoming missions to icy moons, Europa Clipper, Dragonfly to Titan, and JUICE, Jupiter Icy Moons Explorer, aim to characterize subsurface oceans and evaluate their habitability, potentially transforming human understanding of life's distribution in the cosmos. Further advancements in additive manufacturing, 3D printing, have revolutionized industries ranging from aerospace engineering and medicine to construction and consumer products. Innovations such as printing complex metallic alloys, biocompatible tissues, and even complete organ structures from biological materials represent groundbreaking steps toward personalized medicine, advanced manufacturing, and sustainable industrial practices. NASA's exploration of 3D printed habitats on the Moon and Mars exemplifies the profound implications of additive manufacturing for space colonization, infrastructure development, and resource efficiency. Breakthrough research in photonics and quantum optics underpins transformative advances in communications, computing, and sensing technologies. Quantum networks employing entangled photons provide unprecedented security through quantum key distribution, fundamentally altering cybersecurity paradigms. Photonic integrated circuits enable ultra-fast data transfer rates and energy-efficient computing architectures, crucial for next-generation telecommunications and high-performance computing systems. Enhanced optical sensors utilizing quantum principles now offer revolutionary capabilities in medical imaging, gravitational wave detection, environmental monitoring, and precision navigation. Significant strides in computational chemistry and materials simulation enhance predictive capabilities for material properties and chemical reactivity. Leveraging high-performance computing, machine learning, and quantum computing, researchers can rapidly screen and optimize novel materials for energy storage, catalytic processes, pharmaceutical development, and electronic applications. Virtual prototyping via computational modeling accelerates discovery and reduces costs and environmental impacts associated with traditional experimental approaches. Additionally, emerging developments in sustainable chemistry, particularly green chemistry and biomimicry, drive innovation toward environmentally benign and resource-efficient chemical processes. Synthetic pathways inspired by nature, such as artificial enzymes and biomimetic catalysis, facilitate chemical manufacturing with minimal waste and toxicity. Sustainable polymers derived from renewable biomass, biodegradable plastics, and innovative recycling processes exemplify the transformative potential of chemistry to address global environmental concerns. Pioneering efforts in smart cities and urban sustainability have revolutionized approaches to infrastructure development, mobility, and resource management. Integrating the Internet of Things, IoT, AI-driven analytics, renewable energy systems, and decentralized water and waste management solutions, urban planners increasingly design resilient, adaptive, and environmentally harmonious urban environments. Smart transportation solutions, including autonomous vehicles, electrified public transit, and intelligent traffic management systems, promise reductions in emissions, congestion, and urban sprawl, significantly enhancing urban residents' quality of life. Finally, advances in social sciences, notably behavioral economics, psychology, and sociocultural research, increasingly intersect with technology and policy decisions to inform sustainable societal change. Understanding human decision-making, cognitive biases, and cultural norms is essential for designing effective interventions addressing global challenges such as climate change, economic inequality, and public health crises. The integration of these insights into policymaking and education encourages widespread adoption of sustainable behaviors, social cooperation, and collective action toward global well-being. These ongoing discoveries and innovations, driven by interdisciplinary collaboration and technological advancement, continually redefine human potential, addressing complex global challenges and opening unprecedented opportunities for future generations. Further developments in astrophysics and observational cosmology have continued to deepen humanity's comprehension of the universe's structure and origins. The successful launch and operation of powerful observatories such as the James Webb Space Telescope, JWST, and upcoming facilities like the Nancy Grace Roman Space Telescope enhance observational capabilities to probe the earliest epochs of cosmic history, capturing unprecedented views of galaxy formation, stellar evolution, and the initial conditions of the universe. These instruments promise to reveal critical information about the processes underlying cosmic reionization, the nature of dark matter, and the enigmatic forces driving cosmic acceleration. Innovations in gravitational physics also continue to emerge from theoretical advancements and observational breakthroughs. Ongoing efforts to detect primordial gravitational waves, signals dating back to fractions of a second after the Big Bang, aim to test inflationary cosmology and quantum gravity models directly. Advancements in pulsar timing arrays complement existing gravitational wave observatories by exploring ultra-low-frequency gravitational wave signals produced by supermassive black hole mergers, potentially illuminating galaxy evolution and cosmological history. Cutting-edge developments in astroparticle physics, including neutrino astronomy and cosmic ray detection, offer novel observational methods complementing traditional electromagnetic astronomy. Facilities such as IceCube Neutrino Observatory at the South Pole have detected high-energy astrophysical neutrinos originating from distant cosmic sources, providing new insights into violent astrophysical phenomena like active galactic nuclei, gamma-ray bursts, and supernovae. Future neutrino detectors, such as KM3 in the Mediterranean Sea, promise enhanced sensitivity to these elusive particles, opening additional windows onto extreme astrophysical environments and fundamental particle physics. Parallel advancements in computational astrophysics have dramatically increased capabilities to simulate cosmological processes, galaxy formation, and stellar evolution in unprecedented detail. High-performance computing and machine learning-enhanced simulations, such as illustrious TNG and Eagle projects, integrate hydrodynamics, dark matter dynamics, magnetic fields, and star formation physics into highly realistic cosmological models. These sophisticated computational tools provide invaluable insights into cosmic structure formation, helping researchers interpret observational data and refine theoretical models of astrophysical processes. In particle accelerator physics, ongoing research at the Large Hadron Collider, LHC, and plans for next-generation accelerators, such as the Future Circular Collider, FCC, and the International Linear Collider, ILC, offer potential breakthroughs beyond the standard model. These facilities aim to investigate fundamental questions regarding supersymmetry, extraspatial dimensions, dark matter candidates, and the unexplained matter-antimatter asymmetry observed in the universe. Advances in superconducting magnet technology and accelerator design further expand the frontier of particle physics, enabling more powerful, efficient, and precise explorations of subatomic phenomena. Biophysics and biomolecular engineering represent another rapidly advancing interdisciplinary frontier. Researchers combine physical principles with biological systems to understand complex molecular interactions, cellular mechanics, and the physical foundations of life processes. Advances in single-molecule imaging techniques, atomic force microscopy, and cryo-electron microscopy have dramatically enhanced structural insights into proteins, viruses, and molecular machines. These techniques accelerate drug discovery and vaccine development, facilitate bio-inspired materials design, and enable precise engineering of biomolecules for therapeutic purposes. In aerospace technology, breakthroughs in hypersonic propulsion, reusable launch systems, and advanced satellite constellations promise significant leaps forward in space accessibility and global communications infrastructure. Commercial enterprises and governmental programs developing hypersonic vehicles utilizing scramjet engines aim to revolutionize global transportation, dramatically reducing travel times and enabling rapid response capabilities for emergency and humanitarian missions. Reusable rocket technologies pioneered by private aerospace companies drastically lower costs associated with orbital access, enhancing opportunities for space research, tourism, and economic development beyond Earth's atmosphere. Advances in quantum sensing and quantum metrology significantly enhance measurement precision across diverse fields, including navigation, geology, and medical diagnostics. Quantum-enhanced atomic clocks, accelerometers, magnetometers, and gravimeters exploit principles of quantum coherence, entanglement, and interference to achieve unprecedented accuracy and sensitivity. These developments support improvements in global positioning systems, GPS, earthquake detection, geological exploration, and non-invasive biomedical imaging techniques. Breakthroughs in terrestrial ecosystem restoration and ecological engineering also highlight increasingly sophisticated scientific approaches toward addressing biodiversity loss, climate change, and environmental degradation. Ecological restoration projects utilizing innovative methods like rewilding, assisted migration, microbial augmentation, and regenerative agriculture enhance ecosystems' resilience, biodiversity, and productivity. Additionally, bioengineered organisms tailored for bioremediation of pollutants, restoration of degraded landscapes, and carbon sequestration underscore the immense potential of biotechnology and ecological science to rehabilitate Earth's damaged ecosystems effectively. Furthermore, scientific progress in sustainable urban architecture and advanced construction technologies transforms modern infrastructure development. Innovative materials such as self-healing concrete, aerogels, and advanced composite materials offer enhanced energy efficiency, durability, and environmental sustainability. Vertical greening systems, eco-friendly building designs, and urban agriculture integration into urban spaces further contribute to ecological resilience, resource efficiency, and improved quality of urban life. Finally, profound advancements in ethical frameworks, philosophy of science, and responsible innovation practices accompany scientific and technological progress, ensuring its alignment with societal values and global sustainability objectives. Ethical analyses regarding artificial intelligence, genetic engineering, space exploration, and climate intervention practices critically shape policies governing responsible scientific conduct, equitable technology access, and ecological stewardship. Developing transparent and inclusive decision-making processes helps ensure scientific advancements serve humanity's collective interests equitably, sustainably, and responsibly. These extensive and interconnected scientific frontiers continue redefining humanity's relationship with nature, technology, and the cosmos itself, inspiring new generations toward discovery and innovation while collectively addressing pressing global challenges. In conclusion, scientific discovery remains an ever-evolving journey, characterized by continuous exploration, curiosity-driven innovation, and interdisciplinary collaboration. Each breakthrough not only expands humanity's understanding of the universe but also generates transformative technologies, reshapes societies, and challenges existing paradigms of knowledge. The interconnected nature of modern scientific disciplines, ranging from quantum physics and artificial intelligence to biotechnology, environmental science, and cosmology, highlights the necessity of integrating diverse perspectives to effectively address complex global challenges. As humanity progresses, the ethical considerations and responsible stewardship of scientific knowledge become increasingly crucial. Future scientific advancements must carefully balance innovation with sustainability, equity, and ethical responsibility, ensuring that new technologies and insights serve the collective well-being of all global communities. Ultimately, the pursuit of scientific understanding embodies a fundamental human endeavor, driving society toward greater wisdom, resilience, and harmony within an ever-changing universe. HD 189733b is one of the most infamous exoplanets known to science, a gas giant orbiting a star about 64 light-years away in the constellation of Vulpecula. It is a world of extremes, a place where the very concept of weather is taken to an entirely different level. Discovered in 2005 through the transit method, it has become a prime target for exoplanetary studies due to its close proximity to Earth and its large size relative to its parent star, making it one of the easiest exoplanets to observe. The planet orbits its star at an incredibly close distance, completing a full orbit in just 2.2 Earth days. This makes it a hot Jupiter, a class of exoplanets that resemble Jupiter in mass and composition but are far closer to their parent stars than any gas giant in our own solar system. As a result, HD 189733b is exposed to intense stellar radiation, heating its atmosphere to an estimated 1,000 degrees Celsius, 1,832 degrees Fahrenheit. One of the most striking aspects of HD 189733b is its deep blue color, which was determined using data from the Hubble Space Telescope. Unlike Earth's blue sky, which results from Rayleigh scattering in a nitrogen-oxygen atmosphere. The intense coloration of this planet is caused by silicate particles in its atmosphere. These particles, likely in the form of tiny glass droplets, scatter blue light more effectively than red, giving the planet an eerie, ocean-like appearance, though in reality, its surface is anything but hospitable. The atmosphere of HD 189733b is a tempestuous hellscape, featuring some of the most violent weather ever detected on an exoplanet. Observations from the Spitzer Space Telescope and other instruments suggest that this world is battered by winds exceeding 8,700 km per hour, 5,400 miles per hour, more than 7 times the speed of sound. To make matters worse, these deadly winds likely carry molten glass, which rains sideways due to the extreme forces at play. The idea of standing on such a planet, if one could even find solid ground, would be utterly terrifying, with razor-sharp shards of glass swirling through the atmosphere at hypersonic speeds. The planet's dayside and nightside exhibit dramatic temperature differences due to its tidally locked orbit, meaning one side is always facing the star while the other remains in perpetual darkness. The searing hot side can reach around 1,200 degrees Celsius (2,200 degrees Fahrenheit), while the night side, though still incredibly warm by earthly standards, is significantly cooler. This temperature contrast fuels the extreme winds that sweep across the planet, redistributing heat in a violent, chaotic manner. HD 189733b has also provided some of the first evidence of atmospheric evaporation due to stellar radiation. Observations from the Chandra X-ray Observatory and the Hubble Space Telescope have shown that the intense X-ray and ultraviolet radiation from its parent star are stripping away its upper atmosphere. This slow but steady erosion suggests that many hot Jupiters may eventually be reduced to their cores, revealing insights into planetary evolution in extreme environments. Despite its deadly nature, HD 189733b remains a scientific treasure trove. It was among the first exoplanets for which atmospheric water vapor was detected, as well as carbon dioxide and methane, although these gases exist in a toxic, inhospitable mix. The presence of these molecules demonstrates the power of modern telescopes to probe alien atmospheres and search for the chemical signatures of life, even in places where life as we know it could never survive. Its parent star, HD 189733, is a relatively active K-type star slightly cooler and smaller than our Sun. This activity has profound effects on the planet, as stellar flares and bursts of high-energy radiation further erode the atmosphere, creating a dynamic and constantly evolving planetary system. The combination of extreme weather, relentless radiation, and the sheer intensity of conditions on HD 189733b makes it one of the most fascinating exoplanets ever discovered. With future telescopes like the James Webb Space Telescope, astronomers will be able to study its atmosphere in even greater detail, potentially uncovering new and unexpected chemical interactions. Understanding HD 189733b helps refine models of exoplanet atmospheres, particularly for hot Jupiters, which appear to be one of the most common types of exoplanets in the galaxy. Studying these worlds brings us closer to understanding planetary diversity and the possible range of conditions in distant star systems. The exploration of HD 189733b serves as a reminder of the sheer variety of worlds that exist beyond our solar system. It is a place of unimaginable chaos, an alien world that defies expectations, where blue skies do not mean oceans and gentle breezes, but rather a furious storm of deadly winds and glass rain. It is a testament to the extremes of planetary formation and the boundless mysteries of the cosmos. This infernal exoplanet, a monstrous world of extreme conditions, continues to captivate astronomers as they uncover more about its violent nature. The cerulean gas giant, which orbits its parent star in a blisteringly close trajectory, remains one of the most well-studied extrasolar planets due to its accessibility and dramatic atmospheric phenomena. The blistering orb's close proximity to its Sun-like host star ensures that its atmosphere is continuously bombarded with radiation, causing high-altitude storms and chemical interactions rarely seen in our own solar system. Observations of this hellish sphere reveal a composition dominated by hydrogen and helium, but with traces of exotic elements that contribute to its violent weather. Further investigations into the sapphire-hued colossus have revealed that its upper atmosphere contains traces of titanium oxide, a compound that could serve as a potent heat trap. This would explain why the planet's day side reaches such searing temperatures, even though it is only orbiting a relatively cool K-type star. The presence of this compound raises questions about the diversity of chemical processes in hot Jupiters and how their atmospheres evolve over time. New research suggests that the winds on this alien gas behemoth may not only be carrying molten glass, but could also be redistributing atmospheric components in a complex and dynamic way. Infrared observations hint at a turbulent interplay between molecular layers, with heat being transferred in an unpredictable manner across the planet's chaotic skies. Despite the ferocious conditions on this blue titan, it continues to serve as a valuable laboratory for understanding exoplanetary atmospheres. Every new observation of this tormented world sheds light on the behavior of other gas giants found in extreme orbits, paving the way for improved models that could help identify truly Earth-like planets in the future. As astronomers refine their techniques and technology advances, this volatile giant remains a cornerstone in the study of planetary science. The knowledge gained from this turbulent orb helps answer fundamental questions about atmospheric chemistry, heat distribution, and even planetary survival under the relentless assault of stellar radiation. The violent winds that sweep across this azure leviathan at supersonic speeds are a testament to the raw power of exoplanetary weather systems. With each passing year, telescopes reveal new details about its chaotic nature, pushing the boundaries of our understanding. Scientists speculate that deeper layers of this massive celestial wanderer may harbor even more extreme conditions, perhaps exotic forms of matter or deep, roiling currents hidden beneath the cloud tops. As research on this tumultuous gas world continues, it stands as a reminder of the vast, unpredictable nature of the universe. The ongoing study of this sapphire tempest reveals not only its own mysteries but also deepens our understanding of how planets form, evolve, and survive under the most unrelenting conditions imaginable. This tempestuous exoplanet, a colossal roamer of the cosmos, continues to astonish scientists with its unrelenting fury. The more we learn about this indigo inferno, the more it defies expectations, reshaping our understanding of planetary science. Every new observation peels back another layer of its mysteries, revealing a world that seems almost too extreme to exist. The atmosphere of this cerulean maelstrom is a shifting battleground of elements, where chemical reactions unfold at an accelerated pace under the assault of its parent star's radiation. Recent studies suggest that ultraviolet light may be breaking apart molecules in the upper layers, creating a cascade of complex reactions that alter the planet's atmospheric composition in real time. These processes, unseen in our own solar system, hint at a dynamic and ever-changing sky, sculpted by forces beyond anything found on Earth. Deeper within this sapphire juggernaut, the pressure skyrockets to levels that would crush any conventional spacecraft. Theoretically, the intense conditions could give rise to exotic forms of matter, including metallic hydrogen, a phase of hydrogen that behaves as both a liquid and a metal. If present, this material could play a crucial role in the planet's magnetic field, potentially influencing the way it interacts with the powerful stellar winds from its parent star. As astronomers refine their models, new simulations suggest that this volatile colossus may have undergone dramatic evolutionary changes over its lifespan. It is possible that this chaotic gas giant was once even more massive, gradually shedding its outer layers due to the unrelenting radiation from its sun. If true, this means the planet is slowly eroding, losing its atmosphere to space in a process that could one day reduce it to a barren core, an entirely new class of planetary remnant. Despite its inhospitable nature, this storm-racked giant continues to be one of the most scrutinized exoplanets in existence. Scientists are now using cutting-edge instruments, including the James Webb Space Telescope, to probe deeper into its atmosphere, searching for unexpected molecules that could further redefine our understanding of extreme planetary environments. Early results suggest the presence of trace gases that could offer clues about the chemistry of such worlds, potentially revealing new insights into how planets form and what conditions might be necessary for life, albeit in more temperate environments. This sapphire sentinel of the void serves as a stark contrast to Earth, a reminder of just how varied and extreme planetary systems can be. It exists in a state of permanent turmoil, its skies awash with raging storms, searing heat, and an endless cascade of supersonic winds. It is an alien world in every sense, yet it is through the study of such inhospitable places that humanity inches closer to answering some of the most profound questions about the cosmos. As our observational capabilities grow, this violent blue wanderer will remain at the forefront of exoplanetary research, offering an unparalleled window into the forces that shape planets across the galaxy. Every storm, every molecule, every trace of escaping gas tells a story of survival, of destruction, and of the unrelenting chaos that governs worlds beyond our own. This abyssal titan of the cosmos hides secrets beneath its dazzling blue facade, secrets so wild, so alien, that they defy imagination. A place where the skies rip open with molten glass storms, where winds roar faster than a bullet, where the very atmosphere is being torn apart, atom, by the merciless fury of its sun. This is not a world where life could ever exist, but it is a world that refuses to go unnoticed. It is a world that fights to survive. Imagine standing on the edge of an impossible storm, where the sky is not a gentle blue but an electric, violent sapphire, a shimmering illusion, hiding the chaos beneath. The winds are relentless, howling at speeds that could shred metal, carrying with them razor-sharp particles of silicate glass. There is no ground, no surface, no safe haven. Just endless, boiling clouds, roiling in eternal unrest. But the true horror of this celestial beast is not just its storms. It is what lurks deeper. As you descend into the abyss of this gas giant, the pressure mounts with terrifying speed. Gases compress, temperatures soar, and the very air becomes something else, something unknown. In the crushing depths, hydrogen is forced into a metallic state, a shimmering, fluid conductor that may generate a magnetic field unlike anything we have ever encountered. Could this alien world be hiding a core forged under conditions beyond comprehension? A churning heart of metallic storms, locked away from the universe, waiting for the day its outer layers are stripped away. And then there is the slow death, the inevitable fate that awaits this tortured colossus. It is being devoured, its very essence siphoned off into space by its relentless sun. With each passing moment, its atmosphere is eroded by invisible forces, leaving a trail of lost particles in its wake, a ghostly reminder that even giants fall. One day, perhaps millions of years from now, all that may remain of this storm-racked monster is a dense, exposed core, a relic of a once mighty world that fought against the very laws of the universe. But until then, this cosmic tempest will rage on, a beacon of mystery and destruction, a reminder that the universe does not play by our rules. It is a world of extremes, a nightmare sculpted by fire and wind, a place where even the most hardened explorers would find no refuge. And yet, we cannot look away. Because within the chaos of this unrelenting inferno, there are answers. Answers to the origins of planets, to the formation of atmospheres, to the great cosmic ballet that determines which worlds thrive and which are doomed to destruction. And if we can unravel the mysteries of this impossible blue wanderer, perhaps we will inch closer to understanding our own fragile existence in the vast, merciless theater of the cosmos. But what if this world is more than just a doomed giant, more than just a storm-ravaged wasteland of fury and fire? What if, buried within its chaos, lies something we never expected? Something that could rewrite everything we thought we knew about the nature of planets. Imagine for a moment that this violent blue behemoth is not merely a world in decay, but a world in transformation. As it sheds its atmosphere, revealing its raw, exposed heart, could it be something else yet to define? Some theorize this, subjected to relentless radiation and the slow, agonizing loss of their gaseous envelopes, could eventually be stripped down to their very core, leaving behind a scorching, metallic husk orbiting perilously close to its star. A planetary corpse in our solar system. Is Stormborn Day become one of the fabled Chthonian planets, a rock barren remnant, or is there something even at play? Some observations hint at anomalies in the atmosphere colossus, variations, consistencies in the way it absorbs and reflects light. Could there be unknown force beneath its roiling, something shifting in the darkness, unseen? Some exoplanet researchers speculate that in the alien world, strange reactions could be taking place, reactions that defy our models of planetary chemistry. Could bizarre, high-pressure compounds exist here? Chemical combinations never before seen in nature, waiting to be uncovered by future missions. Could this world be a crucible, a place where new elements or even exotic states of matter form under unimaginable conditions? And what of the storms themselves? Their terrifying speeds, their razor-sharp, could there be some planets have hidden and buried deep, turbulent what their distance, blue hurricane, a heart of thing fueling its eternal tempests. And then there's the ultimate question, the question that lingers in the minds of those who dare to study such an unforgiving place. What if this is not the most extreme world out there? If a place like this can exist, if nature can forge a planet where glass rains from the sky and winds scream faster than sound, then what else is lurking in the endless dark of the cosmos? Perhaps this electric blue monster is merely a preview, a glimpse of even greater, more terrifying worlds that await discovery. Perhaps, out there, among the billions of planets that remain unseen, there are giants where storms crackle with plasma, where magnetic fields twist reality itself, where entire atmospheres collapse and reform in a matter of days. If we can barely fathom the horrors of this deep azure maelstrom, what unspeakable forces might exist on planets more extreme than this? And yet, we cannot turn away. There is a pull, a gravity to this world beyond the literal. It beckons us to understand, to unravel its riddles, to push the boundaries of what we know. It is a reminder that the universe does not cater to human comfort. It is brutal, it is wild, and it is beautiful. And for all its violence, this world is a wonder, a masterpiece of chaos sculpted by the unrelenting hand of the cosmos itself. We are only beginning to scratch the surface. The more we look, the more we realize, we are still standing on the threshold of discovery. What lies beyond is darker, stranger, and more thrilling than we ever imagined. But what if this blue inferno is hiding something even more profound, something waiting to be uncovered by the next wave of explorers who dare to peer deeper? The secrets of this celestial leviathan are not just locked within its howling storms or its searing heat. They might be written into the very fabric of its existence. What if its violent past holds a clue to how planets live and die? What if it was not always the tortured colossus we see today? Some astronomers theorize that this sapphire tempest may have once been part of a grand cosmic migration, a planet born in a distant, colder region of its solar system, only to be dragged inward by gravitational forces in a cataclysmic spiral toward its star. If true, this means it wasn't always a hellscape. There may have been a time, long before it was scalded by radiation and stripped by the stellar winds, when this gas giant was a serene, distant wanderer, drifting through the outer reaches of its system. But then came the fall. Perhaps an ancient gravitational dance with another planet, or even an unseen force, an interstellar rogue, a passing star, disrupted the balance, flinging this doomed titan toward its present, perilous orbit. The closer it came, the worse it became. The heat intensified, the atmosphere swelled, and the very chemistry of the planet was rewritten by the relentless pull of its new, fiery master. The transformation was violent, irreversible. And now, it is locked in an unending nightmare, too close to escape, too large to burn away completely, caught in a cosmic purgatory. But what if it is not alone in its suffering? If one world can undergo such a brutal transformation, how many others are out there, enduring the same fate? Are there legions of tortured giants orbiting their stars in agony, each one slowly unraveling, their atmospheres ripped away molecule by molecule? Could some of these gas giants be in the final throes of their existence, on the verge of collapsing into exposed, molten remnants, or even, if pushed too far, being completely consumed by their own stars? And here is where the true mystery begins. If a world like this can be reshaped so violently by the forces around it, what does that mean for planets like Earth? We like to believe our world is stable, that our orbit is fixed, that our position in the solar system is permanent. But the cosmos does not care for such illusions. We now know that planetary systems are not always as orderly as we once thought. Planets migrate. They collide. They are ejected into the abyss or pulled into destruction. It has happened before, and it will happen again. This tortured giant may be showing us our own future, not in the form of fire and wind, but in the cold, indifferent truth that no world, not even our own, is immune to the chaos of the universe. And so, we continue to watch, to measure, to listen. Because every storm that rages across this blue titan, every molecule that escapes its grasp, every anomaly that challenges our understanding, it all brings us closer to the answers we seek. Perhaps the greatest lesson this world teaches us is not just about the nature of exoplanets, but about our own fragility. That even the mightiest planets can be humbled. That nothing lasts forever. That the universe is as merciless as it is magnificent. And that somewhere, out there, in the infinite dark, even greater revelations await. But what if this is only the beginning? What if this colossal blue beast is not just a victim of cosmic forces, but a harbinger of something far greater, something we have yet to grasp? Every storm that howls across its atmosphere, every molecule lost to the void, every superheated gust of wind that tears through its skies, is telling us a story. A story of transformation, destruction, and perhaps even rebirth. But what if this story is not unique? What if there are others? Some astronomers believe that worlds like this are not rare but common, scattered throughout the galaxy, hidden in the glare of their stars, waiting to be found. What if this tortured giant is merely one in an unseen legion of planets undergoing the same violent metamorphosis? Could we be witnessing an entire class of worlds evolving before our eyes, planets that were never meant to stay the same, but to be reshaped, over and over, by the relentless hand of time? And what if this transformation is not the end, but a gateway to something new? For years, we have searched for exoplanets that defy explanation, planets with impossible densities, strange orbits, compositions that do not match our models. What if some of these anomalies are the missing pieces of a larger puzzle? What if these erratic, unexplainable worlds are the remnants of once massive gas giants, stripped down to their enigmatic cores, surviving long after the storms have passed? Some researchers have suggested that beneath the swirling chaos of this world, a solid core may already be taking shape, a planetary skeleton, forged in the fires of its own destruction. What happens when the last wisps of its atmosphere are gone? Will it become something new, something unknown, something we have yet to name? Could this be the fate of all hot Jupiters, a slow, agonizing collapse into a rocky husk, drifting in silence where once there was fury? Or is there another fate awaiting this deep blue leviathan, one even more catastrophic? Some gas giants, if pushed too close to their stars, do not survive. They do not simply erode, they are devoured, swallowed whole by the very sun they once orbited. Could this world be on that path? Is it inching closer with each passing eon, its orbit tightening, its days numbered? Will there come a moment, perhaps millions of years from now, when its final remnants spiral inward, vanishing forever into the inferno of its star? And if so, how will it end? Will it be slow, drawn out over millennia, a gradual thinning until nothing remains but a ghost of gas, lost to space? Or will there be one final, desperate moment, a cataclysmic plunge into the abyss, a last defiant burst of light as it is consumed? Will it leave behind a trace, a signature in the spectrum of its star, a faint whisper of a planet that once was? Or will it be as if it never existed at all? We do not yet know the answers. We do not yet know how this story ends. But we do know this: whatever fate awaits this sapphire inferno, it is not alone. There are countless others like it, some already lost, some still burning, some yet to be discovered. And as we continue our search, as we push further into the unknown, we are left with a haunting thought: if planets can be destroyed, if they can be devoured, rewritten, erased, then what does that mean for us? Are we watching the future of other worlds? Or are we, in some distant way, watching our own. Or perhaps, just perhaps, this sapphire giant is not merely a victim, not merely a dying world spiraling toward oblivion, but something else entirely. What if this planet, this whirling vortex of chaos, holds within it an answer to a question we have not yet dared to ask? We assume that planets, once formed, are static, unchanging islands in the cosmic sea, bound by the laws of physics to follow their prescribed paths. But what if that is not true? What if some planets, like this restless behemoth, are not just passive celestial bodies, but active players in their own evolution? Look deeper into its atmosphere, beyond the storms, beyond the searing winds that slice through its endless twilight. There is something strange happening here, something unsettling. The heat patterns do not behave as they should. The atmospheric composition is shifting in ways we do not fully understand. The light that bounces from its clouds carries hints of something unexpected, something unaccounted for. Is this planet truly dying, or is it becoming something else? Some models suggest that, under extreme conditions, gas giants like this one may not simply erode, but transmute, undergoing a metamorphosis so violent, so profound, that it shatters our very definition of what a planet is. What if, buried deep beneath its toxic haze, new elements are being forged, materials that have never been seen before, created under pressures and temperatures beyond anything found in the natural world? Could the very act of its destruction be an act of creation? Or could this planet be part of a cycle, a process that repeats across the universe, unseen and unmeasured? What if we are looking at a cosmic alchemy, a transformation that takes eons to complete? Could there be others, planets that were once like this one, now unrecognizable, reborn as entirely new celestial bodies? We see rocky worlds in impossible places, molten remnants that should not exist, dense objects that seem to defy their own formation. What if they, too, were once giants, now stripped to their cores, forged into something new by the relentless crucible of time? And then, the question we dare not ask, what if there is intelligence in this transformation? Not life as we know it. No biological entities could survive the nightmares raging across this world's surface. But what if the planet itself, or something within it, is adapting? Changing? Resisting? Some astrophysicists have speculated on the existence of self-regulating planetary systems, worlds that, in some incomprehensible way, react to their environments, altering their own chemistry, manipulating their own atmospheres in response to external threats. Could this deep blue colossus be doing just that? Could it be fighting back against its own demise, shifting its composition in a desperate bid to survive? Or is something else acting upon it? There are things we have yet to explain, phenomena we detect across the cosmos that do not fit within our frameworks of understanding. We see energy signatures we cannot identify, gravitational anomalies that defy prediction. What if, in the depths of this planetary hurricane, there are forces at work that go beyond what we have ever encountered? What if this planet is not just a lesson in destruction, but a warning? We search the skies for habitable worlds, for places that remind us of Earth, for new homes dark. But what if the truly important, the ones that resemble our ones that show us the other side, the ones that demonstrate the fates we never considered? The ones that arrogance, our certainty, our understand how the universe works. What if this brilliant blue inferno is one of those planets? A signal, a marker, a mystery we are not yet ready to solve. And as we continue to watch, to study, to measure its unrelenting chaos, we must ask ourselves, what happens when we finally understand what we are looking at? And will we be ready for the answer? Or perhaps, the answer has been staring us in the face all along. What if this howling, sky-blue tempest is not just an anomaly, not just a curiosity in the vast cosmic sea, but a testament to something far older, far more deliberate than we ever imagined? We assume this planet is alone in its suffering, a world locked in a battle with its own fate, caught in the unrelenting grip of its parent star. But what if it is not alone? What if there are others? What if this deep blue juggernaut is part of a hidden pattern, one we have only just begun to perceive? Consider this: throughout the galaxy, we have detected planets in extreme orbits, worlds that burn, worlds that freeze, worlds that should not exist where they do. But scattered among them are gas giants eerily similar to this one, hot, raging, and doomed. They, too, orbit too close. They, too, are unraveling, their atmospheres ripped away, their surfaces tormented by forces beyond their control. What if they are not just a coincidence? What if they are remnants? What if we are looking at the scars of something ancient, something that has left its mark on planetary systems across the galaxy? Some astronomers have speculated that the orbits of these tortured giants suggest a history of violent interactions, hidden gravitational upheavals that have reshaped entire solar systems. Could there have been unseen cataclysms in the past, wars between worlds, celestial upheavals that forced planets like this one from their rightful places, sending them spiraling toward oblivion? What if this planet was never meant to be here? What if it was flung into the fire by something we have yet to understand? There is a mystery lurking in the data, one that has haunted researchers as they map the strange and seemingly chaotic arrangements of exoplanets in other systems. Some of these worlds appear displaced, as if they were moved, altered, scattered. There are planets that orbit in ways that make no sense, massive giants that should have devoured their neighbors but remain strangely alone, rogue planets drifting between stars, severed from their origins. Could they all be connected? Could they be the remnants of something long past, a lost event, an ancient mechanism, a war, a purge, a cataclysm that left only these silent, screaming survivors as evidence? And if so, what was the cause? We assume planets are passive, that they are shaped only by the natural forces of gravity, heat, and time. But what if that assumption is wrong? What if something else, something we do not yet comprehend, has played a role in shaping them? What if there was once a time when planetary systems were not as they are now? What if, in some distant epoch, there were forces moving planets, altering their fates, deciding which would remain and which would be cast into the fire? And what if we are only now beginning to see the scars of that forgotten age? This tortured, cerulean world may be a window into that past, a living relic of a process we do not yet have the words to describe. It may be a warning, a survivor, a message written across the skies in storms of molten glass and winds that scream through the void. It may be the key to a secret that has been hidden among the stars for longer than we have existed. And as we continue to watch, to probe its depths, to unravel its mysteries, we must ask ourselves one final question: what if we are not just studying this planet? What if, in some distant way, it is studying us? And what if, in the vast, unrelenting silence of space, something else is watching too? We assume that we are alone in our curiosity, that we are the first minds to peer into the abyss and wonder at the nature of this tortured world. But what if this deep blue sentinel, this storm-ravaged giant, is not merely an object of study, but a beacon? A signal. A marker left in the cosmic dark, its very existence a monument to something older, something we have yet to recognize. Look at the way its atmosphere shifts, not just in response to its star, but in ways that defy expectation. The winds do not simply move, they accelerate, churn, spiral in chaotic patterns that suggest an underlying force, something more than just heat and gravity at play. Some researchers have already noted irregularities in its atmospheric data, tiny deviations, unexplained fluctuations in its chemical makeup, as if something beneath its clouds is not simply reacting to its environment, but altering it. Is this planet trying to communicate? Not in words, not in language as we understand it. But in its storms, in its vanishing gases, in the way it resists its own destruction, could there be an encoded message? A relic of something we have yet to decode? What if this planet is not just dying, but performing? We have always assumed that intelligent life must take the form of beings like us, creatures that walk, speak, build. But what if intelligence can take other forms? What if it can be planetary? What if this gas giant, with its swirling, restless chaos, is not simply a world, but a system, a machine, a vast and ancient construct designed for a purpose we have yet to understand? Some scientists have speculated that the most advanced civilizations would not leave ruins or artifacts, but entire planetary-scale modifications, changes in the chemistry of worlds, in their orbits, in their very fabric. Could this planet be such a creation? Or worse, could it be a warning? What if this deep blue behemoth was not always like this? What if it was something else before, something vibrant, something alive? What if, long ago, it was transformed, reshaped, reforged into the nightmare we see today? By what? By whom? And for what purpose? The deeper we look into the cosmos, the more we realize how little we understand. We have mapped only a fraction of the planets in our galaxy, and yet we are already confronted with mysteries that seem impossible. Rogue worlds drifting without stars, pulsars flashing in eerie, deliberate intervals, objects moving in ways that should not be possible. What if this planet, this howling, glass-raining, sky-blue titan, is part of something bigger? What if it is part of a message, a structure, a pattern written across the universe itself? And what if we are not just observers in this grand unfolding mystery? What if, from somewhere in the endless dark, something is waiting for us to understand? And when we finally do, when we finally see the truth, what happens next? And what if, when we finally decipher the truth, it is already too late? What if this brilliant blue inferno is not just an enigma, not just a celestial oddity, but a countdown? A cosmic scar left behind by something we cannot yet comprehend? We have spent decades gazing outward, searching the stars for signs of life, for civilizations, for proof that we are not alone. But what if the answers were never hidden in distant, Earth-like worlds? What if they were buried in the wreckage of planets like this one, twisted, burning husks of what they once were? What if this deep azure monster is not a mistake of nature, but an echo of something that came before? We see only what remains, the storms, the shrieking winds, the endless erosion of its atmosphere. But what if, long ago, before the fires consumed it, before it was flung into the jaws of its star, this planet was something else? A world of order, of structure, of intention. A world that was destroyed. Not by chance. Not by time. But by something else. And what if the same fate awaits others? Consider this: we have only just begun to uncover the story of exoplanets. We are infants in our understanding, limited by our instruments, by our distance, by the brief span of time we have been able to observe the universe. What if there are clues we have missed? What if we are staring at the wreckage of something vast, something ancient, and not even realizing it? We have found strange things in our search, planets that should not exist, worlds whose compositions defy physics, star systems with missing giants, as if something erased them entirely. Could this seething blue world be a missing piece of that puzzle? And if so, what does it mean for us? We have always assumed that extinction is a local phenomenon. That civilizations rise and fall on their own, that planets are shaped by the natural forces around them. But what if we are wrong? What if extinction can be engineered? What if entire worlds can be erased, not by natural disaster, not by war, but by something older, something vast, something cold and patient that moves unseen between the stars? What if we are not the first to wonder about this planet's fate? What if others before us saw it, studied it, tried to understand what happened here? And what if they, too, disappeared? There is a chilling thought that lingers at the edges of this mystery, the idea that we are looking at a message written in the ruins of a planet, a warning carved in wind and fire, a whisper from something we cannot yet name. And if we listen too closely, if we learn too much, do we risk becoming part of that message? Are we staring into the abyss of a planet's death, or are we staring into our own future? And if something out there is watching us, waiting for us to understand, what happens when we do? And if something out there is watching us, waiting for us to understand, what happens when we do? What if, at the very moment we unravel the secrets of this planet, we trigger something we were never meant to find? What if this blue storm, this glass-raining inferno, is not just a warning, but a test? A beacon, a trap, or perhaps, an invitation. We have spent centuries believing that knowledge is our greatest strength, that understanding the universe is the key to our survival. But what if some knowledge is forbidden, not because it is unknowable, but because knowing it brings consequences? What if this planet, this tortured remnant of something long lost, is the last echo of a civilization that once stood where we now stand, on the edge of revelation, peering too deep, asking the wrong questions? Perhaps it was never meant to be found. Perhaps it was hidden for a reason. And now, by looking at it, by searching for its secrets, by pulling at the threads of its unraveling existence, we are waking something up. What if we are not the first to look upon this dying world with curiosity? What if others have come before us? Other civilizations, rising from their home planets, staring at the stars, asking the same questions we ask now. What if they, too, reached a point where they discovered places like this, ruined, burning giants, whispering of an untold past? What if they, too, studied these lost planets, eager to decipher their riddles, to unlock their mysteries? And what if they are gone now? Not because they destroyed themselves. Not because their civilizations fell to war, or disease, or time. But because something came for them. Because they looked too closely. Because they saw something they were never meant to see. What if this planet is not just a record of destruction, but a doorway? A silent, waiting door. One that only opens when the right questions are asked, when the right discoveries are made. A door that does not lead to knowledge, but to something else, something vast, something cold, something that does not care about curiosity, or ambition, or the fragile hopes of species that dare to seek the truth. What if, as we observe this world, as we study its dying breath, something else is studying us? And what if, at this very moment, as we speak of it, as we search deeper, it has already begun to take notice? Perhaps this world has waited for something like us to come along. Perhaps it has waited for this moment, for this cycle to repeat once more. Perhaps its story does not end in fire and wind and silence. Perhaps its story is about to begin again. And perhaps, this time, we are the ones who will be written into it. Make, one of the fascinating trans-Neptunian objects in our solar system, stands as a key member of the distant Kuiper Belt, a region of icy bodies located beyond the orbit of Neptune. This dwarf planet, formally recognized by the International Astronomical Union (IAU) in 2008, has intrigued astronomers since its discovery due to its unique combination of physical, chemical, and orbital characteristics. Discovered on March 31, 2005, by a team led by Michael E. Brown, Chad Trujillo, and David Rabinowitz, this enigmatic world has become a focal point of study for understanding the outer reaches of the solar system. Make's name is derived from the mythology of the Rapa Nui people, the indigenous inhabitants of Easter Island. In their culture, Make is a creator deity, an appropriate name for a celestial body that opens new chapters in humanity's understanding of the cosmos. This remote world, often described as a Plutoid because of its similarities to Pluto, provides critical insights into the formation and evolution of the solar system's outer regions. With a diameter of approximately 1,430 kilometers, Make ranks as the third largest known dwarf planet in the solar system, following Pluto and Eris. Its size, though modest compared to planets, is substantial enough to allow its gravity to shape it into a roughly spherical form. This classification criterion, along with its orbit around the Sun and its inability to clear its orbital path of debris, secures its status as a dwarf planet under the IAU's definition. Observations of Make have revealed an intriguing surface composition dominated by methane, ethane, and other hydrocarbons, which are thought to give the dwarf planet its reddish hue. Spectroscopic studies conducted using ground-based telescopes, such as the Very Large Telescope, VLT, in Chile, have been instrumental in identifying these compounds. The presence of methane ice, in particular, draws parallels with both Pluto and Neptune's moon Triton, suggesting commonalities in the processes that shape these distant objects. The surface of this distant world is believed to be extremely cold, with temperatures averaging around -243 degrees Celsius. At such frigid temperatures, volatiles like nitrogen and methane freeze solid, forming an icy crust that reflects sunlight with a moderate degree of brightness. Make's albedo, or reflectivity, is higher than that of most other Kuiper Belt objects, KBOs, which has aided in its detection and characterization. Make orbits the Sun at an average distance of about 45.7 astronomical units, AU, equivalent to roughly 6.8 billion kilometers. Its elliptical orbit takes it around the Sun once every 305 Earth years, with a slight inclination of 29 degrees relative to the plane of the solar system. This inclined trajectory places Make among the dynamically hot KBOs, which have orbits more tilted and eccentric than the cold classical KBOs like Quaoar. One of the most intriguing aspects of this Kuiper Belt object is its lack of a significant atmosphere. Unlike Pluto, which experiences seasonal atmospheric changes due to the sublimation of nitrogen and methane ices, Make's tenuous atmosphere, if present at all, is likely composed of trace amounts of methane and nitrogen. Observations during stellar occultations, when the dwarf planet passes in front of a distant star, have provided valuable constraints on its atmospheric properties. These events reveal a sharp drop in brightness, indicative of a lack of a substantial gaseous envelope. In 2016, the Hubble Space Telescope made a groundbreaking discovery by identifying a small moon orbiting Makemake. This satellite, unofficially nicknamed 2 Malawian Kwachas, is estimated to have a diameter of about 175 kilometers. It's the trans-Neptunian body, known as Makemake, stands as a remarkable example of the icy worlds populating the outer reaches of our solar system. This celestial object, part of the Kuiper Belt, occupies a region teeming with primordial remnants from the early formation of the Sun and its planetary system. Since its discovery in 2005 by a team of astronomers led by Michael E. Brown, the frozen sphere has captivated scientists eager to unravel the mysteries of these distant and enigmatic objects. This dwarf planet, the third largest among its peers, boasts a diameter of approximately 1,430 kilometers, situating it in the same category as Pluto and Eris. Unlike the inner rocky planets or the gas giants, the icy surface of this world is composed primarily of frozen methane, ethane, and other hydrocarbons, which give it a reddish hue. Spectroscopic analyses, carried out with advanced telescopes like the Very Large Telescope, VLT, in Chile, have been pivotal in uncovering the chemical composition of the Kuiper Belt object. Orbiting at an average distance of 45.7 astronomical units, AU, from the Sun, this remote sphere takes approximately 305 Earth years to complete a single orbit. Its elliptical path, inclined by 29 degrees relative to the ecliptic plane, distinguishes it from many other solar system objects. These orbital characteristics classify the icy body as part of the dynamically hot population of the Kuiper Belt, where orbits tend to be more eccentric and inclined than the cold population. Interestingly, this far-off world exhibits a surface that is highly reflective, with an albedo higher than that of most other trans-Neptunian objects. This bright reflectivity, coupled with its size, made it a relatively easier target for telescopes to detect compared to smaller, darker Kuiper Belt objects. Its icy crust, composed of solidified methane and nitrogen, reflects sunlight with a unique reddish tint, linking this distant body to other notable objects like Pluto and Triton, Neptune's large moon. Unlike Pluto, however, this celestial body lacks a significant atmosphere. Stellar occultations, events where the icy sphere passes in front of a background star, have revealed that it does not possess the thick layers of nitrogen and methane gas seen on its sibling dwarf planet. At its average surface temperature of -243 degrees Celsius, any gases would freeze rapidly, leaving only a tenuous, almost imperceptible envelope of methane molecules. Adding to the intrigue, in 2016, astronomers using the Hubble Space Telescope uncovered a faint satellite orbiting this frozen world. The Moon, provisionally labeled 2 Malawian Kwachas, is estimated to be about 175 kilometers in diameter. The discovery of this satellite has opened new doors for research, allowing scientists to measure the mass and density of the dwarf planet with greater precision. By observing the orbital dynamics of 2 Malawian Kwachas, researchers aim to gain deeper insights into the internal structure of this trans-Neptunian object and its formation history. The discovery of this moon also hints at the possibility that this distant body underwent a significant collision event in the past, similar to the impacts theorized for other dwarf planets and their moons. Such events are thought to have played a critical role in shaping the Kuiper Belt as we observe it today, providing clues to the early chaotic phase of the solar system's evolution. This icy world's methane-rich surface composition links it chemically to Pluto and Triton, suggesting a shared evolutionary pathway for these distant objects. Methane, one of the simplest hydrocarbons, plays a vital role in determining the color and reflectivity of this frigid world. The reddish hue observed on its surface is likely the result of complex organic molecules, known as tholins, formed through the interaction of methane with ultraviolet radiation from the Sun. These tholins are common on outer solar system bodies and are responsible for the strikingly varied colors of trans-Neptunian objects. Scientists hypothesized that the distant sphere's lack of significant nitrogen ice might be due to its smaller size and weaker gravity, which would make it more difficult for the object to retain lighter gases over billions of years. This hypothesis contrasts sharply with Pluto, which has managed to sustain a thin but dynamic nitrogen-rich atmosphere. The comparative study of these worlds offers a glimpse into the diversity of conditions and evolutionary pathways among objects in the outer solar system. Further investigations into this Kuiper belt member have been bolstered by advanced telescopic technologies and computational modeling. Observations using infrared spectroscopy have provided evidence for seasonal changes on the surface of this frozen sphere. These changes, though far less dynamic than those on Earth or Mars, hint at subtle shifts in the distribution of ices as the dwarf planet travels through its elongated orbit around the Sun. The exploration of this enigmatic object has also fueled discussions about potential spacecraft missions to the Kuiper belt. While current missions, such as NASA's New Horizons probe, have provided invaluable data on similar bodies, a dedicated mission to this dwarf planet and its moon could revolutionize our understanding of the outer solar system. By studying this world up close, scientists could analyze its geology, surface chemistry, and potential subsurface layers, answering long-standing questions about the building blocks of planets and the processes that govern their evolution. This frozen world, residing in the cold and distant reaches of the solar system, represents a time capsule of early solar system materials. Its study not only sheds light on the dynamics of the Kuiper belt but also provides broader insights into the mechanisms that drive planetary formation and migration. Through ongoing research and future exploration, the mysteries of this icy body continue to inspire curiosity and expand the boundaries of human knowledge. The frozen orb stands as a crucial key to understanding the broader landscape of the Kuiper belt, a region that serves as a repository for ancient materials from the dawn of the solar system. Unlike the rocky planets of the inner solar system or the gas giants further out, this remote celestial body represents a category of icy worlds that formed in the outermost reaches, where the sun's warmth is but a faint glow. Its composition, structure, and orbit together create a unique portrait of conditions far removed from those familiar to earthbound observers. One of the remarkable features of this Kuiper belt resident is its stability over time. Despite its vast distance from the Sun and its relatively small size, the dwarf planet has maintained a consistent orbital path for billions of years. This stability has allowed astronomers to study the interactions between it and other trans-Neptunian objects, offering critical insights into the gravitational dynamics of the outer solar system. The inclined orbit of this icy body, with its significant tilt compared to the plane of the solar system, suggests a turbulent past. It is likely that gravitational interactions with Neptune, or perhaps with other large Kuiper belt objects, played a role in shaping its current trajectory. The absence of significant atmospherics on this distant sphere has not deterred scientists from probing its surface for clues about its evolutionary history. High-resolution imaging and spectroscopy have revealed a patchwork of icy materials, including solid methane and ethane, alongside traces of more complex organic molecules. These compounds, while frozen solid under the extreme cold, bear evidence of photochemical reactions driven by the faint sunlight and cosmic rays that permeate the outer solar system. The reddish tint that characterizes its surface is a hallmark of such processes, with tholins, organic residues formed from methane, providing the distinctive coloration. Further exploration of this icy sphere's surface has revealed intriguing hints about its geological processes. While its small size and low gravity likely prevent tectonic activity or large-scale volcanism, there is evidence to suggest that sublimation and deposition cycles may occur on a seasonal basis. As the frozen world moves closer to the Sun in its elliptical orbit, some of its methane and nitrogen ices could transition directly from solid to gas, creating transient atmospheric effects or causing slight changes in the surface texture. These processes, though subtle, are of immense interest to planetary scientists, as they mirror phenomena observed on other Kuiper Belt objects like Pluto. The discovery of a small satellite orbiting this celestial object has added a new layer of complexity to its study. 2 Malawian Quachas, as the Moon is informally known, is much darker than its parent body, reflecting only a fraction of the sunlight. This stark contrast in albedo suggests that the Moon and its host may have originated under different circumstances. One prevailing theory is that the satellite was formed as a result of a massive collision, similar to the events that are thought to have created Pluto's moon system. Such a collision would have ejected material from the surface of the icy world, which later coalesced to form the smaller companion. The existence of 2 Malawian Quachas also provides astronomers with a unique tool for studying the mass and density of the frozen orb. By carefully tracking the motion of the Moon around its primary, scientists can calculate the mass of the entire system, shedding light on its internal composition. Early estimates suggest that the density of this Kuiper Belt resident is lower than that of Pluto but higher than some smaller trans-Neptunian objects, implying a mixture of rock and ice in its interior. These findings hint at a layered structure, with denser materials concentrated in the core and lighter ices forming the outer shell. In addition to its intrinsic scientific value, the study of this remote celestial body holds broader implications for understanding the history of our solar system. The Kuiper Belt, of which this dwarf planet is a part, is believed to be a remnant of the primordial disk of gas and dust that gave rise to the Sun and its planets. By analyzing the composition and distribution of these icy objects, researchers can reconstruct the conditions that prevailed during the early stages of planetary formation. This frozen sphere, with its pristine ices and unaltered surface features, serves as a time capsule preserving the chemical and physical processes that shaped the solar system's infancy. The implications of studying this distant world extend beyond the confines of our solar system. Similar icy bodies are thought to populate the outer regions of other planetary systems, where they may serve as building blocks for planets or as reservoirs of water and organic materials. Understanding the processes that govern the evolution of this frozen orb can therefore provide valuable insights into the potential habitability of exoplanetary systems and the origins of life elsewhere in the universe. Despite its remoteness, this trans-Neptunian body remains within reach of modern astronomy. Ground-based telescopes equipped with adaptive optics, as well as space-based observatories like the James Webb Space Telescope, continue to provide detailed observations of its surface and surroundings. These instruments have opened new windows into the chemistry and physics of the frozen world, revealing intricate details that were once beyond the reach of human knowledge. Future missions to this icy sphere